Okay, can people hear me over the mic now? Okay, good. Let's, I guess, get started. First of all, any questions about anything related to graph algorithms or scheduling or homework or something like that? You guys should have the graph algorithms homework. You should be starting to think about that. Are there any questions about the homework that people have come up? Again, on the homework, there are a bunch of paper problems, which you should, of course, do in teams with your partner. There is a little programming assignment where you're asked to use depth-first search or breadth-first search to just basically test the connectivity of graphs. And this is something I encourage you to actually, each of you, make sure you know how to do it. If you can't, that should make a lot of this sort of adjacency of matrix, adjacency list manipulation much more transparent, and it's important to sort of see where that comes from. Any questions? Okay, any questions at all? Okay, so what I'd like to talk about is I'd like to continue our discussions from last class, where we were talking about minimum spanning trees. Minimum spanning trees were, remember, we had a weighted graph, and we wanted to find what was the subset of edges that left a connected graph, okay, that was a tree, such that the sum of the edge weights was as small as possible. And that was what we meant by a minimum spanning tree. And we showed that you could use depth-first search or breadth-first search to find a spanning tree, but that ignored the cost of the edges. If we wanted to try to find one of minimum weight, we had this idea, I guess, of Prim's algorithm, which if I take a look over here, just to remind ourselves what the algorithm is, I guess we can go back here, is that we are going to repeatedly select vertices, grow our tree one vertex at a time, where at each point we're going to pick which vertex can we add to the tree at minimum cost, namely by the lowest weight edge possible. That was what Prim's algorithm was supposed to be doing. Okay? Any questions about that? So just to remind us, again, I went through the execution just quickly. Let's see if this is going to work any better than yesterday. I started at one arbitrary. Let's start at a different vertex. That might be an interesting thing to do. I start at some vertex of my graph. Let's see if this is going to work. Unfortunately, it doesn't look like it's going to work today. Possibly even worse than last time. Hold on. Is there no way to make this give me color? Okay. I want to say it looks like the red ink is empty and the blue ink is empty. Okay, so it looks like we are not able to. Let's just try one more time. Let's say clear ink. Let's say kabunk. And let's just try this. Okay. So it looks like this is broken now, officially. Okay, so what is what is Prim's algorithm going to do? Let's try to take a look at the graph that we have up there. Let's say we start from the upper right-hand corner of that, the vertex that has the 5 and the 2 in it. In each iteration, we are going to grow by adding an edge, okay? Grow by adding a edge of minimum weight connecting the tree that we have to what we don't have. Does everybody see that? So starting from the upper right vertex, which would be the first edge that we add? It's going to be of weight what? 2. Now we've got those 2 vertices in our tree. The next edge we're going to add is going to be of weight 2. And now we've got that upper triangle here. And the next edge we're going to add is of weight 3. Okay, 3 everyone agrees is less than 4. Okay, 3 we're going to add, and now we've got that center vertex. And the next vertex we're going to add is of weight 4. And then the next one we're going to add is of weight 7. It could be why won't we add the weight of age 4? Because again, you can't see it because my pen is broken. But basically we have the other edge of vertex of that already in the tree and adding that edge of weight 4 to the weights of edge 2 and 3 that we already have will create a cycle. Correct? Does everybody see that? Okay? And then now we have a choice. We could add one of the 7 edges. What's interesting is once we add the one of weight 7, what is the next smallest edge that we can add? Okay? 5. Does everybody see that once we add one of those 7s, that'll either connect to A or the one at the other end of that 5. Once that's there, we can now add, instead of adding the other 7, we'll add the cheaper edge, the 5 one. Any questions about that? Okay? So this is Prim's algorithm. We're starting from a different vertex. If this algorithm is correct, it had better give us the same weight spanning tree. Okay? Any questions about that? Okay. Well, what does it mean? Okay, so there's a question now here, which is, I think now we're going to go to the board, because now we're going to start having a deep question we're wrestling with. Is I think people know how Prim's algorithm is supposed to work. Okay? It's not obvious, not hard to see what it's actually supposed to be doing. But there's a question is it right? Okay? Does it always give us a minimum spanning tree? It should be clear that if the algorithm is correct, starting prims from one vertex or the other shouldn't change the weight of the tree that it builds. Prim's algorithm says start from a vertex and do this procedure. If starting from a different vertex, it gave us a tree of different weight, then it is not a correct algorithm. Does everybody agree with that? It does not mean that we're going to necessarily get exactly the same tree, because as we've noticed, for certain graphs, there might be multiple different minimum spanning trees for it. Does everybody recognize that? If I gave you a graph where every edge was of weight 1, any spanning tree was a minimum spanning tree. Okay? So we've got a couple of considerations here that have to go in it. Okay? My question now is, can we figure out, can we argue that Prim's algorithm is in fact correct? That this procedure always gives us a minimum spanning tree. Okay? That's really the important question here. Any questions? So why is Prim's algorithm? Let's try to work this thing out now a little bit. Here I've got a graph. It's a weighted graph. You know, you do your thing. This is chunk, chunk, chunk. Let's say there's weights on here. Prim's algorithm says always start growing from here. Why is Prim's algorithm correct? Can anybody give me some reasoning as to why Prim's algorithm has to give us a minimum spanning tree? It's a pretty simple algorithm to walk through. I think that much everybody agrees. Can anybody argue why it is correct or propose why it's correct? Okay, on every possible graph. Okay, any ideas? Yes. Yeah. Okay, so you're saying at every point we're always taking the lowest cost edge that goes from the tree outside the tree, and therefore it's correct. The trouble is that's the exact same argument you would use to prove that the greedy procedure works for traveling salesmen. But it doesn't work for traveling salesmen. Okay? Does everybody see that there is something non-trivial here going on? Okay? It is certainly true that at every point we're picking the cheapest possible edge. But the question is, how do we know we don't get into a trap? Okay? We want to pick the globally best spanning tree. Yes?
By picking the lowest, or the edge of the lowest numbers or whatever, first, you're going to exhaust all other edges and all other ways to get there before picking. So therefore, if let's say some edge has a degree with a very high number, you'll see it from every other edge on that graph. You'll graph out its point, so what has the lowest path from there first.
Okay.
See the lowest number that connects to that one.
Again, I don't hear anything, maybe, but I don't hear anything here that says anything different. You could say the same thing for traveling salesmen. And always picking the cheapest edge to go on your traveling salesman tour. And you're probably saying the exact same thing. Okay? And for that, it doesn't work. Okay? There's kind of an amazing thing here with minimum spanning tree. Is that, in fact, making this greedy decision, I claim, is you're never going to go wrong. Okay? And we're going to need a real proof of this. Any other ideas before we go through it? Yeah? Okay, that's fair enough. Let me now tell you how I prove it. Okay, it's not obvious you should be able to prove it on the fly. But let's think what my argument is. When I try to prove things, again, in general, there are two ways to prove things that computer scientists know how to prove. They can prove it by induction, or they can prove it by contradiction. Okay? Here I am going to claim, let's try to prove it by contradiction. Okay? Now, what is a contradiction proof going to be? A contradiction proof says that assume that the algorithm is wrong. Okay? And then let's work out the consequences of this assumption and see that we have gotten into trouble by doing so. That is what a proof by contradiction is. Correct? So what is a proof of contradiction? If Kruskall's algorithm is wrong, then there must be some graph on which it is wrong. Right? Yeah? You're going to propose a graph where it's wrong? Okay, well, let's talk about that. What graph is it wrong?
If you give one where, let's say it's shaped like a hexadecimal or something, and you start at one point where it would be like 2 to go up, and then 1 to go over a point that has degree, it'd be 0.
Draw it. Okay, now, again, bear in mind that Prim's algorithm is correct, so your example is going to be wrong, but it's a good example of it. Draw it. Yes, do it. Do it. Okay? But I think that's a good thing to do anyway. Okay? Okay, not to put, it's educational. That's what I mean. That's why we're doing this, right? Let's look at this. Okay, so I don't want to get your hopes up here. Okay, good. So yeah. Okay, so you're saying, what is Prim's algorithm going to do here? Okay? The important thing is, first of all, what is the minimum spanning tree of this graph going to be? It's going to ignore the 5. What is Prim's algorithm going to do? Actually, Prim's is going to have a nice time with this one, right? I mean, from here, because what it's going to do is say the cheapest thing adjacent to me is this. The cheapest thing adjacent to me is this. The cheapest thing adjacent to me is this. The cheapest thing adjacent to me is that. Does everybody see that that's what Prim's algorithm is going to do? Okay? And in this case, it's going to, it's always grabbing the vertex that is connected to it that it can get to as cheaply as possible. So you agree on this example, Prim's algorithm is going to do the right thing, right? Okay, good. So what is my argument that Prim's algorithm is correct? Okay? It is going to be a proof by contradiction. And for a proof by contradiction, I'm going to say, you got me. Prim's algorithm is wrong. If it's wrong, what does it mean? It means there must be some graph where it fails. Okay? Now, is it going to fail to give me a tree? No. Because I am always going to keep picking vertices until everything I get a tree from it. Okay? So certainly Prim's algorithm, if the graph is connected, is going to give me a tree. That there's no doubt about it. The question is really, is it the minimum spanning tree? So if we think that this is, if in fact your algorithm is going to tell me that there is a counterexample, I'll say, show me the graph. Here is the graph where Prim's goes wrong. Okay? And let's think what Prim's is going to do. Prim's is going to start from some vertex. You can tell me where I want to start. And it's going to start adding the cheapest edge, the cheapest edge, the cheapest edge. And at some point when I do that, it's going to, a bell is going to go off. Ding, 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 ding. What has happened? If Prim's algorithm is going to make a mistake on this graph, is not going to give me the minimum spanning tree, at some point I must have made a lethal mistake, okay, where adding this edge was fatal. because there is no minimum spanning tree containing all the edges that I have added so far. Okay, does everybody agree with that? If Prim's algorithm was correct, it would never pick an edge that would cause a fatal problem, because it's always going to give me a spanning tree. But if Prim's algorithm is incorrect, then as it picks edges, at some point it will have gotten edges here, okay, such that there is no possible minimum spanning tree that includes these edges and some combination of the rest of the graph, okay? And I'm going to say, is that so? Okay? Well, why don't you then tell me, a wise one, what the minimum spanning tree was? Okay? And the minimum spanning tree had to have this edge, had to have this edge, couldn't have this edge because I made a mistake, right? This is where I went wrong, right? So in fact, it must have had other edges. And let's say that the way that they finished the minimum spanning tree happened to look like this, okay? Let's say this and this, okay? And they will say, aha, this is the minimum spanning tree and you didn't find it, okay? And I'm going to say, is that so, okay? Well, what do we know about, you're telling me I shouldn't have picked this edge. What happens, however, if I now add this edge back to the graph, okay, to your tree? Adding an edge to a tree is going to do what? What happens when you add an edge to a tree? Yeah? It makes a graph. It was a graph, okay? What happens, though, when you add an edge to a tree? What do you get? A cycle. That's what it's going to make, right? If I added this edge to my graph, where did I get a cycle? Okay? Does everybody agree? I guess my cycle was presumably ka-chunk, 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 ka-chunk. Does everybody see that? Now, suppose I were to take away this edge. That was the one that, suppose I were to now, having added that edge, I created a cycle. Suppose I now take away this edge. Is the graph still going to be a tree? Is the minimum spanning tree still going to be connected? Let's think about this. So what is my situation? There was this tree that was made partially of edges I picked and edges after it said I went wrong. When I added back the edge that I thought went wrong, that I added that they told me went wrong, that created a cycle in the tree. Note that if I remove this, if I add back my edge and remove any edge on the cycle, the tree is going to stay connected. Let me draw that in another picture because it's sort of obvious. Here is a tree. Okay? I have now added this edge to it. Note that if I delete any edge from the cycle, the tree is still connected. Does everybody see that? If I delete this one, it is still connected, right? What if I delete this edge? Is it still connected? No, but why not? It wasn't part of the cycle, right? So when I add this edge back to my tree, it creates a cycle. Note that I could delete any edge from that cycle, and I would still have a spanning tree. Does everybody agree with that? This may sound long-winded, but this should now be obvious. Now my ask question is this, what if we take, if we look at this cycle, there is going to be an edge that was adjacent to the part of the tree that I had already built. If you look at this, let's say our situation was, this was in my spanning tree, this was in my spanning tree. When I went to choose this edge, I did what? I picked the smallest weight edge that connected these three vertices to the rest of the graph. Isn't that what Prim's algorithm did? what do I know about this green edge on the cycle? Okay? Yeah? It has to be of weight greater than or equal to this thing. Why is that? Well, I had a choice here of any edge connecting one vertex that was in the tree to something outside the tree. In picking the cheapest, I picked this one. I had the freedom to pick this one. Right? Does everybody see that? Because I didn't pick this one when I had the freedom to do so, this edge must be of weight less than or equal to that edge. And so what does that mean? That means that this green thing with this two edges couldn't have been a minimum spanning tree. Because by putting in my edge and taking out this edge, the cost can only go down. Does everybody see that? That's the contradiction here. You're saying Prim's algorithm did not give me a minimum spanning tree. I'm saying, oh yeah, give me the spanning tree that you gave that you think is minimum for this. I will show you that the first place where Prims diverged, where you picked an edge that I wouldn't have picked, I would come up with a better tree, or at least a no worse tree, by putting in my edge and taking out the one on the cycle that was adjacent back to the tree that I had so far. How many people get that idea? Okay, any questions about this proof? That is why this has to be correct. Okay? Any questions about it? Okay? This is actually kind of amazing because very few things in this class will we see. We're constantly picking the best next thing gives us the globally optimal solution. And minimum spanning tree happens to be one of them. That's one reason why we're excited about this. Any questions about the proof or anything like that? Yes?
How would you write that up?
How would I write that up? Well, one thing I would do is go to my textbook and read the section, and then you see exactly how I would have written it up. Okay? So that would be my first instinct. But the basic idea is you would write it as a proof by contradiction. Okay? Assume the opposite. The opposite means Prim's algorithm, there exists a graph where Prim's algorithm doesn't give you the graph. Okay? Therefore, on that graph, there is a point at which you first pick it on Prim's edge. Okay? If so, now take what would have been that Prim's edge I would have picked and union it back to the graph. That creates a cycle. There is going to have to be a higher weight edge, or at least a not lower cost edge, that you could replace my edge with so that the weight of the total tree is going to be less than that, okay, or less than or no greater than that, which meant that my Prim's algorithm did not make a mistake here, okay, or you made a mistake here. Any questions here? That's kind of how I would write it up. Any questions about it? And again, read the book to see exactly how I wrote it up. Any questions? Okay? So this is actually an important point, okay? Prim's algorithm is provably correct, okay? Okay, so now we have a way to find, again, this is basically the picture here. Again, I can't unfortunately write, it doesn't look like I can today write on my, my thing, but again, you can see what this is saying here. If you look at the basic flow, x to y over there was me making what seemingly was the fatal mistake of picking up Prim's edge. And I say, no, 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 no. When you add that Prim's edge to your tree, it creates a cycle. That edge V1 to V2 was something I could have picked when I chose to pick X, Y. But I didn't, okay? So therefore, edge V1, V2 is uglier than edge X, Y, okay? And switching them yields a spanning tree of no more of weight, no worse than what you tell me the best one is. Any questions? Okay, good. So Prim's algorithm is correct, and you can't do an argument like that for traveling salesmen. Now, why can't you do an argument like that for traveling salesmen? Well, I guess you've got to show me an argument here. It sort of says that, again, somehow fundamental to this is this idea that you're saying that I made a mistake by picking this, and that whatever tour you come back with, when I add this back, there's no way to fix it. That simply isn't true for traveling salesmen. Any questions? Okay. So how fast is, by now you should believe the correctness of Prim's algorithm. How fast is Prim's algorithm? It should be clear that, that it is an algorithm of the basic form, okay? Start from a vertex, which is, vertex 1. N times we're going to go around and pick the smallest weight edge between the tree and the non-tree parts. Okay? My claim is it should be obvious we can find what the smallest weight edge is between the tree and the non-tree things if we keep a Boolean vector that for every vertex I will tell you whether it is in the tree or not. Okay? Suppose we have an array of Booleans where in tree sub I is true if and only if vertex I is in the tree. Originally, only the start vertex is in the tree and everybody else is not. Then in each iteration, we're going to add another vertex to the tree. That's going to be done by flipping the bit, okay, to say now vertex I is now in the tree. To figure out what the smallest weight is to add next, we're going to want to do it if we did a walk over all the edges in the graph, all the m edges in the graph, and asked ourselves, do the endpoints, if this is an edge from I to j, is vertex I in the tree and vertex j not in the tree? Good, then that's an edge we can consider. Then let's keep track of which is the cheapest such edge. If both edges are in the tree, we're not going to want to consider it because that would create a cycle. Both endpoints were in the tree. Adding this edge would create a cycle. If both endpoints are not in the tree, then we can't add this edge yet because it's not adjacent to our tree, right? So my claim is it should be clear that in order m time, we can sweep through to figure out what the next edge to add is. And this would give us an n times m implementation of Prim's algorithm. How many people see that? How many people don't see that or have a question? I don't understand where this running time comes from. Any questions? Okay. So if that's true, what I'm going to tell you is, in fact, there is actually a faster implementation. And it's going to, for us to do this faster, we're going to have to do a faster job identifying what the minimum weight edge is between the tree and the fringe. Okay? Does everybody kind of see that? Okay? We're still going to have to make n iterations. But if we can find a data structure that will make it easier to identify which edge is the cheapest between the fringe and between the tree and the non-tree, okay? If we could do this in order n time, then we would have an order n times n or an n squared algorithm, which would be better than n times m. Any questions about that? Okay. To do this, let me explain the idea before I show you the code, because I think it's going to be kind of a, the idea is, not that complicated. What we're going to do now is, what is our problem? We have got, in general, in the middle of our execution, we started from some vertex S. We've got some cloud of vertices that are in our tree. We have got some other cloud of vertices that are in what I will call the fringe. The fringe are the ones that are within one edge of being in the tree. Then we've got other vertices that are even further removed. Okay, and I shouldn't have a cloud around them, but they're not in the fringe. Maybe, well, let's just put them here anyway. Does everybody see that if we start a growing process here, we start growing from Bohemia, Long Island, right? The things that are within one hop of Bohemia, Long Island are other Long Island cities, right? San Francisco is not within one hop of it, right? But as we grow and grow, in general, there's some vertices that are in our tree. Okay, the tree may look like this. There's some vertices that are within one edge of it. And there's other vertices that are not within one edge of it. Okay? Prim's algorithm wants to, for all the vertices that are in this fringe, wants to find the cheapest way to link them to this tree. The next thing that we want to do is the cheapest edge that links a vertex from the fringe to the tree. Okay? Any questions about that? What if we keep track for every vertex, okay, what is the cost of linking it to the tree right now? Okay? San Francisco and all other vertices that are too far away, the cost of linking these vertices in is infinite. Does everybody see that? There's no single edge that will do it. But what we could do for every vertex that is in the fringe, we could know what is the cheapest way of getting it in there so far. Okay? Suppose these are vertices 1, 2, 3, 4, and 5. Let's say that there is a way of getting vertex 1 into the tree at a cost of 9. There's a way of getting vertex 2 into the tree at a cost of 7. There's a way of getting vertex 3 into the tree at a cost of 3. There is vertex 4 at a cost of, let's say, 6. And vertex 5 at the cost of, let's say, 8. Which is the next vertex that we will bring into the tree? We need to just simply look at this array, which for every vertex tells us the cheapest way to get it into the tree. And we will decide in order n time, since there's at most n vertices in the fringe, to grab vertex 3. Does everybody see that? Once we grab vertex 3, how can we now update it to know what the cheapest cost is to get every other vertex into the tree? This is actually the crux of it now. Suppose this array is keeping track of the cheapest way of getting these vertices into the tree. Once we have added 3 in, what updates have to happen to this? Yes?
We can check the edge weight between 3 and every other vertex in the graph.
Right, so the only things that will change is now we have the option of going through 3. Does everybody see that? There might be a super highway to San Francisco, which happens to be vertex 6, right? And we may have finally discovered a way of doing that, which happens to cost 10, okay? Or there might be an edge from 3 to some other vertex, like 5. Suppose there is an edge from 3 to 5 of weight 4. Then we have discovered a cheaper way to link 5 into the tree. Does everybody see that? So what is the basic idea here? This is going to keep track of the cheapest way we have so far of getting every vertex in. To find what is the next guy to add, we pick which is the next vertex, the lowest weight one. Way to get a vertex that is not in the tree in, that's order n. To update it after we have added another vertex, we're going to look out at all the outgoing edges to see if they give us a new, cheaper way to add some other vertex of interest. Does everybody see that? And so these are n rounds of find the minimum one that is in the minimum way to link another vertex in, and then figure out the consequences for it by updating these distances for any vertex we have found a cheaper way to get into the graph. How many people are with me? Any questions about it? Okay. If you believe that, let's now look at the code and see how you do this. Okay. What is Prim's algorithm going to do? We're going to keep track of a couple of different things. There is a Boolean vector, int, which for every vertex will tell us, is the vertex already in our spanning tree or not? There is a distance measure, which is going to tell us what is the cost of the cheapest way we know of to add that vertex to our tree. Okay? And then there's some bookkeeping variables. So what is our initialization? For every vertex originally, the cost of linking it to the tree is infinite. Okay? The way it got into the tree, the parent, which is what we used like from Bedford search and depth first search, is nil because it's not in the tree. And because it's not in the tree, we say that int tree is false. Okay? That's the initialization. The distance to the starting vertex. We're going to do prims from a particular starting vertex. To add the starting vertex to the tree costs us 0, because that's where we're starting from. Any questions about the initialization? The basic part of this, if you look at it, is there are two phases of it. There's an outer while loop that's going to go around, okay, n times, one to bring in each vertex. V is going to be the last vertex we brought in. V is originally to start. The first clump of code we have here is for trying to figure out which is the what is the consequences of adding V to the tree. Well, int tree sub V is going to be true because now it is V is in the tree. We're then going to go through V's adjacency list, okay, and say, well, that is not nil, meaning for every edge in V's adjacency list, let's say y is the corresponding vertex, okay. The weight of that for every edge is going to be a weight. The weight is equal to that edge's weight. If the weight of going to vertex W, okay, if the weight of this edge from V to W is less than the weight, than the cheapest way we know of to link W into the tree, and W is not in the tree, then we have found a new, cheaper way of linking W into the tree. And so the distance to W, the cost of linking W in potentially is weight, and the way to do it is through V. Okay? Any questions about that? So this first clump is updating the consequences by going through all outgoing edges of the newly added vertex V. The second clump here, is now going to say which is the next vertex that we want to add. And what is the point? Well, we're going to go through all n vertices. Okay? And if vertex I is not in the tree, and if the cost of getting into, of linking I into the tree, okay, is the cheapest edge we know of so far. Originally we start with maxint. We're going to keep looking at all ones. This is just going to find the minimum of all the distance matrix for all vertices that are not yet in the tree. Okay? It should be clear this takes n time. It should be clear that the top part takes the degree time, which is at most n. N plus n is n, and we're going through this a total of n times. This gives us an n-squared algorithm, implementation of Prim's algorithm. Any questions about that? Okay, how many people think they get it? Okay, this is worth getting it, because in a few minutes we're going to see that you really need to have gotten it, because you're going to see it almost exactly the same thing again. Okay, so it pays to get it now, so you'll understand it the next time. Any questions? Okay, does everybody see now? You should now see we can compute minimum spanning trees efficiently. Prim's algorithm is always going to be correct. Okay, and we can do it in n-squared time with the right bookkeeping. Any questions about that? Okay, any questions at all? Okay, I normally talk about another minimum spanning tree algorithm here. But I am going to try a little bit of a change here. Okay? Any questions right now about minimum spanning trees? I reserve the right to go back to minimum spanning trees later, but at the moment I want to try something different. Okay, kabunk, clear. Let me just get out of here. What is this thing? Oh, suddenly it's writing? What is this? Okay, let's just do this a little bit. Okay, well, we've got the freedom. Okay, that's maybe interesting to know. Any questions? Clear ink. Oh, I can do it with my mouse. That was what the difference was. Okay, maybe I can figure that out.
You can go back and select.
What did I have to do?
Go to Smarting and click select.
Go to what? I'm sorry.
The thing you clicked on to clear.
Clear.
Yeah, but
Bunk.
click select. Just
Select. Bunk.
You might have to click the pointer.
the actual little picture.
What little picture? I hate to.
You were just over it.
This?
Click to the left. The arrow next to the word select.
Select picture. Okay, now you're telling me if I do this, it'll go away? No. And I want to make this thing go away. X, bunk. Very good. Thank you. You should be teaching the class. Okay? Good. Sorry about this. For what it's worth, I've done this several times. I've taught in this room several times, and every year I get I could go through an orientation for them to show me how to use this, but always fail. Okay, let's look at the problem of the day now. Okay, just to make sure we know about minimum spanning trees and think a little bit more about that. Suppose that we are given we have a graph G with n vertices and m edges, and we are given the minimum spanning tree of it. Okay, let's see if I can make this, if I can draw now. Is that right? So here, no. Is this right? Unselect, what is it? Oh, I've got to select pen. I see, bunk. Good for you. Okay, so let's say that I am given a minimum spanning tree of a graph. This happens to be it. Okay, kabunk, kabunk. There's a graph here on n vertices and m edges. And I'm given a new edge. Let's go to the color here. Okay, I'm given a new edge. Bunk. A new edge. Okay, that I'm going to add to my graph. Can you give me an efficient algorithm to find the minimum spanning tree of the graph plus the edge? Okay? Yes?
Perform a breadth first search until you find, starting from, so you have a new edge you're adding, so start at either the start or the end vertex of that edge.
Start here, and you want to do a breadth first search. Ka-chunk, 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 ka-chunk. And once I have discovered that, okay, yeah?
You want to, and when you're doing the breadth first search, you want to keep track of the edge along that path with the longest weight. And then once you find the other vertex that is a part of the edge, you remove the edge with the longest weight that you found along the path.
Okay, so what he's saying, he said one thing that is right and one thing that I'm going to quibble about. Okay? What he's saying here is, if I'm given the spanning tree and I am told, oh, here's another edge you might have used, how do we update the correctness of the spanning tree? What he was saying was, find the cycle that is formed by adding that edge, right? Or equivalently, the path in the tree between the two endpoints. How many if you have a tree, how many paths are there between any two vertices in a tree? Exactly one. This is one nice property of a tree. Okay? So he's saying find the path from here to there, find the biggest edge on that path, and if the biggest edge on that path is bigger than the edge that you want to add this vertex and delete that. Does everybody agree with him that that's correct? Now, what's my quibble with him? He was saying breadth first search. Okay? Now, maybe kind of, okay, but I like depth first search for finding cycles, right? Because A breadth-first search, you said keep track of the smallest path on here. It's a little hard to know what that actually is, because in the course of breadth-first search, you're visiting a bunch of edges potentially active, right? But if I start from here and I say do a depth-first search, add the edge, well, okay. So what I might have done is add the edge, okay? Find the cycle, and then figure out what the smallest edge is on the cycle and delete it. That's what I would have done with depth-first search. If not, regardless, the key issue is find the smallest weight edge on the path from here to there. Okay? Any questions? Yes?
It says it should run in O n, but isn't depth-first and depth-first n plus n?
Okay, so this says, wait, it's got to run in order n time. And depth-first search is order n plus m, where m is the size of the graph. What's the problem? In this graph, right now, we've thrown away everything but the spanning tree and one extra edge. The spanning tree has how many edges in it? N minus 1. N minus 1 plus n is n. So n plus n is, some people would say 2n. I would say n. Right? Does everybody see that this is a sparse graph? Because it's a graph doing a depth-first search on a linear number of edges, where the number of edges is linear and the number of vertices would be order n. So that's why we get away with order n. Any questions about that? Does everybody see that? Now, what if I were to do something dirtier? This graph says you are given an edge, what we would call it. Let's just make this a little more complicated. You're given a graph with n vertices and m edges. Okay, suppose, let's say now, instead of adding an edge, we are told we could delete an edge, to delete a specific edge. How much time will it take to update the spanning tree if I delete a particular edge? Okay, does everybody see it? The graph G has n vertices and m edges. I am given the tree, I am given G. I am now told, take out this edge from the graph. How does the minimum spanning tree change, and how would I update that? Okay. Do people see what my problem is? I am now giving you, again, I hope I can draw this now, although maybe not, a big complicated graph where I've got a minimum spanning tree in red. I've got all other edges in my graph. Okay, let's say what else I have, conjunct. I am now going to say delete a particular edge. Now find the minimum spanning tree of what is left. Okay? Can anybody tell me about this one? Yeah?
You would have to choose the edge that the edge with the least weight that would connect the now two components that would connect.
Okay, does everybody see that if I delete an edge that was not part of my minimum spanning tree, obviously the minimum spanning tree does not change, right? If you delete a very expensive road from, the road that is very expensive, my minimum spanning tree doesn't change. But what happens if the edge that you delete, in fact, is in the minimum spanning tree, this one here? What am I going to do to update it? Well, after I delete it, I've got two components here. I've got deleting an edge from the minimum spanning tree will create two connected components in the graph. Any edge that spans that, adding any edge that spans those two components would make it a tree again. So what edge do I want to add? The cheapest such edge. Does everybody see that? So how much time will this take to do in a graph of n vertices and m edges? Now the graph is not necessarily sparse, right? Before, the tree by itself had n edges. But the graph you gave me, in general, that I found the minimum spanning tree on, had m edges. I'm deleting an edge from the graph. If that edge happens to be in the minimum spanning tree, the minimum spanning tree has changed. Okay, and now I've got to find the cheapest thing spanning the components. How would I do that? Yeah? So what you're saying is, oh, if I delete these two, if I delete this edge, don't I only have to consider edges that are adjacent to this vertex or that vertex? The answer is absolutely not. Okay, why not? Again, I'm hating this this device, but look, let's just go through that. That should be clear. Okay. So, you know, suppose I've got a minimum spanning tree like this. Let's say here is my minimum, here is my minimum spanning tree. Okay. If we delete this, this edge, okay, you're saying I only need to consider edges that go from this potentially or from this potentially. Does everybody see that? That's what you're suggesting. And that obviously is not right, because in fact the cheapest weight edge might very well have been this guy. Right? Yes?
I was going to say, to check a total of m minus n edges, the remaining ones that are there.
Check all the edges. And how much time does it take to check whether an edge is going to span the components? Well, let's think how we could do this. It's actually an interesting question. So now I've got two components, right? We agree that I'm going to now do a search through all the edges in the graph originally, right? And find out what the weight of that edge is. The real question that's going to be hard is, does that edge span the two components? Okay? One way to do it is to add the edge back and see if it's connected. That would mean for each one of these m tests that I'm going to do, it would be n plus m time to run a connectivity test, right? Is there a faster way, however, to check whether or not an edge is going to span these two? Yeah? Okay, the way I would say this is the following. Suppose I keep for every vertex, I find out what the connected components are. And I build an array for each vertex that tells me what component I am in right now. Does everybody see that? All of these vertices are in component 1, all of these vertices are in component 2. Under what condition is an edge going to be interesting to me? Yeah? If it goes from 1 to 2, does everybody see that? And now then, to say, is edge I to j potentially interesting? I look at the ith value, I look at the jth value. If they are different, then that edge is interesting to me. Does everybody see that now it's going to be m tests, each of which takes constant time? How many people see what I'm saying? How many people do not see what I'm saying and want to see that? It's okay to want something. Okay, yes? How long will it take to build this data structure? Well, how long does it take to take a graph and find the connected components of it if it has n vertices and m edges? Yeah? N plus m. So in n plus m time, I could do the component test. I could find the components, right? In the course of doing that, if you remember what I'm doing, every time I can label every vertex with what component number it's in. So in n plus m time, I can build this thing, right? Now, once I have this, I can then spend order m time to finish the job, right? Then it's going to be this plus m times order 1. So the total time of this operation is going to be n plus m, building this structure. Any questions about that? Okay. Any questions? Okay. So thinking about, again, the way to think about spanning trees, minimum spanning trees, are to recognize that adding edges creates cycles. You want to make sure you never put the heaviest weight, keep the heaviest edge on any cycle. Okay. Any questions about that? Okay. Bingo. Okay. Clear ink. Kabunk. Okay. What I'd like to talk about now is the weighted graph problem that everybody knows, okay? Although you don't know how to find it, okay? And that's finding shortest paths, okay? The classic practical occurs every day problem on weighted graph is given two nodes in a graph. Find the shortest path between them. You need to do this in your GPS. Your GPS needs to do this, right? There's a lot of problems where these things, so I guess the GPS doing it is what I've got here, the transportation problem. There happen to be an amazing number of other problems that come up in algorithms that reduce to shortest path problems. Today, at 10:30 in the morning, I had an electrical engineer walk into my door. Okay, I didn't get nervous. It was scheduled. Okay? But what did this guy want from me? Okay? This guy came in and started saying to me, I want to optimize the phases of, on a power line, there's three-phase power, and I want to balance the loads, and I want to find the best possible way so that the loads are as even as possible. And he talked, and we reasoned, and blah, blah, blah. Ultimately, what was his problem? His problem was build this particular graph and find the shortest path on it. Okay? There are an amazing number of problems in the universe that reduce to taking a graph, taking the problem, describing it by a graph, and finding what is the shortest path on that graph. The key is making sure that the vertices mean something and the edges mean something, and the weights of those edges mean something. Okay? And so we're going to be interested in shortest path for a couple of different reasons. One is, like I say, transportation, and I will say communications problems. When you're routing a packet between one place and someplace in a network, ideally you want it to follow a shortest path, just as much as when you're driving from here to Poughkeepsie, you want the shortest path. Okay? Any questions about it? So let me talk here about, I want to make this kind of point very, very clear that, as an algorithms person, what is it that you're going to learn here from this class that you can take with you? What I wanted you to take with you is to look for shortest path problems, okay? That a lot of different applications on things that you're going to be asked to do will reduce to finding shortest paths, okay? And learning to smell this is more important than trying to design your own algorithm. Let me give you one case in point, okay? And this is another work that we did at one point on where we were looking at, again, you guys now all are surgically attached to cell phones, okay? Now, in the olden days, cell phones only keys that they had were on the front were the telephone keys. Who here still has a primitive enough phone where that happens? Okay, good. So they exist, okay? And back then, just like you guys are busy trying to type into your cell phone, people wanted to type into cell phones, and the problem was that they could only type in the digits 0 through 9. And they wanted to type text, and they wanted to type it in English. And in English, you have 26 letters. Is everybody aware of that? Okay? So what did we want to do? We wanted to build a system where we could take as input streams of phone digits. Somebody could type in 1 digit per character they wanted to type. They could hit the asterisk for a space, and we would figure out what text they meant to type, okay, as a way of efficiently entering text on a telephone. Any questions about what the setup is? Okay? Why is this problem not trivial? Okay, to try to figure out what words somebody meant to type from their telephone key, yeah? There are 3 letters on every digit of your phone. Does everybody agree with that? So when you type in the word boy, okay, what? 4 on some. In general, there are 3 letters on each one. When you type in boy, you hit the same sequence of tokens as if you hit box, which is the same sequence of tokens as if you hit any, which is the same sequence of tokens as if you hit cow. Okay? Does everybody get that idea? So which one of these words did you mean to type? Okay? You can't figure it out just by yourself. You may be wanting to have a discussion about farms or a discussion about dating, or I don't know. But that's a difference between which one you mean, right? So how did we figure it out? We wanted to look at the entire sentence, the entire stream of things you typed in, to help interpret which symbol you had. We could certainly take a dictionary, all the words in English, and map them to their phone tokens. Therefore, when you typed in a word that was in the dictionary, we knew what words were compatible with those phone tokens between the two asterisks. Does everybody see that? Our problem is that we've got several possible words that could stand for that symbol. And we wanted to try to make an accurate guess as to which word you meant to type. So how did we do that? Okay. We said, let's build a graph out of it. What's the graph? Well, graphs have to have vertices and edges. The vertices of my graph are going to be, for every slot in my possible sentence, what words in the dictionary are compatible with it. In this case, it was give and hive. In this case, again, you can't read it because I can't read it. It was of and me, okay? In this case, In this case, it was ring, sing, and something else, right? Now, let's think about, we've got vertices 1, 2, 3, 4, 5, 6, 7, 8 vertices. We've got an edge between every adjacent pair of words in the sentence. Does everybody see that? If we think about that, then an interpretation of the sentence is exactly a path in the graph. How many people here see what I mean by a sentence being an interpretation? Okay, a path in the graph. Any questions? And if we gave weights to the edges, the best interpretation logically is the shortest weight path through the graph. Does everybody get that idea? If we can give weights to reflect what the likely transitions are, then we can hope that the shortest path might tell us something. What would govern, do you think, how likely the transition is from give to me? Okay, what weight should we give to that? Or, yeah?
You probably build some sort of Markov chain from some sort of sample of
We could look at a zillion English sentences. A zillion was smaller back then because we didn't have as big a corpus as you would easily get today. But if we looked at a lot of English sentences, we could look at, for the word give, how many words were there, how often was the next word me? Okay, word me may have occurred 3 times. Give cow, how many times did that pair occur? Probably not very often, right? Okay? So you could build a matrix, for example, about how likely it was that you went from one word to the subsequent word, right? Anything else we might want to factor in there? Okay? Okay, it seems clear that the word pair transition seems to be like the big thing. Okay? We could also use other things like the part of speech. Certain words are nouns, and nouns, you may have a noun is rare, but noun verb is more common, right? But bottom line, we can boil all that down into the cost of the edge, okay? And if you do that, then it is natural that the question of what reconstructed sentence is it? It is the shortest path in this matrix, in this graph, okay? Any questions about that? Yes?
Wouldn't it be possible that if you added some additional words to the sentence that could radically change what the shortest path is through that and thus change the interpretation of...
What do you mean by adding some other words to a sentence?
I mean, while the sentence is still being typed, or is the shortest path...
So here we were reconstructing the path after you finished typing.
All right.
Okay? So you're right. If you did it as a partial way, then you're probably right. You might say that the best, if you just typed in 2 words, it would pick the shortest edge, right? But that might get you to a word when you had 3 words in, when you consider the third word. Suddenly there may not be a cheap edge from that word interpretation to something that's a possibility in the third word, right? Yeah. And then suddenly you would reconstruct the whole path. So you're right, as you include more and more words, the earlier path, shortest path might change. That's exactly right. But that's why finding the globally optimal shortest path gives a meaningful interpretation. Any questions? Yeah?
How would you know when one word begins and one word ends?
Okay, so the way we did this is here, we had them type in a asterisk. Okay, you have on your phone, you had the 12 things, there was also the pound and the asterisk. Okay? And so that was supposed to indicate end of word. Okay? Although if you didn't want to do that, you could conceivably have still broken the string up into words wherever you saw a word match, and then connect edges, okay, between successive words. But anyway, that's how we did it. We used a space character. Any questions? And when we did this, we ended up getting 99% of all characters right, okay, when you interpret it. So you could read the message when you entered it this way. Any questions about it? This is the moral here is that if you can find the shortest path, okay, a lot of problems can be modeled as shortest paths. Any questions about that? Okay, so let's talk a little bit about finding shortest paths. Okay, how do we find shortest paths? Okay, first, suppose the graph is unweighted. Okay, if I give you a graph where all edges are weighted equally, what is the best way to find the shortest path between vertex I and j? What is the right way for an unweighted graph? Okay. Yes. Breadth first search. Remember, breadth first, if it's an unweighted graph, meaning all edges have equal weight, the one with the smallest number of ops is the shortest path, correct? That is exactly what we found with breadth first search. So, if you want to find a shortest path in an unweighted graph, that's BFS. We can do that in linear time. And we're perfectly happy with that, right? Any questions? Okay. Now, note that in general, the shortest path might not involve the minimum number of edges. Consider a kind of a world like this, where that was one edge in a graph. And maybe we add let's say this is vertex A. I'm afraid this is it, and this is B. Maybe there was one edge that was very, very long. It might be that a shorter path may involve 1, 2, 3 edges from A to B. Okay? So if you have weights on the edges, this property is no longer true. Any questions about that? Okay? You might say, well, why don't you find all shortest paths between a graph? Okay? And then pick the smallest. Or maybe just print out all shortest paths. This turns out to be something you can't do because the number of shortest paths can be exponential. Suppose we have a graph that is made of where you've got 2 choices to go here, and 2 choices to go there, and 2 choices to go here. I know this is bad. To get from here to here, you could either go up or down, and then up or down, or then up or down. There's 2 to the n ways you can get to here if you have n of those widgets, right? So there can be exponential number of paths, all of them of the same weight. You can't list all shortest paths. You have to be content with finding a shortest path. Any questions about that? Okay. Let me give you one other weirdness about shortest paths in weighted graphs. Okay, that should be obvious. Is that funny things can happen when you have negative weight edges. Okay? Suppose, let's say that, kabunk, let's try it like that. Suppose we have a graph where the weight of the edge was going to be the cost of traveling on it. Okay? So let's say we've got a graph that looks like, let's say, this. Okay? And the cost of driving on a road is what? Usually If there was a toll, I guess it would be the toll, right? But what if, but usually it's the cost in gasoline. So if we measured it in pennies, maybe if this was a short road, it might take 2 cents of gas to drive here, 1 cent of gas to drive there, 3 cents of gas to drive there, 1 cent of gas to drive there, 2 cents to drive here, 2 cents to drive here. However, what happens if over here they were running a special and giving away ice cream cones? Maybe the store had just opened up. Okay? Have everybody ever seen you go to an ice cream store, the first day they'll give you an ice cream cone? Suppose an ice cream cone cost 5 cents. Okay? Meaning the cost of, normally would cost 5 cents. If they're giving you a free ice cream cone for going by the store, what's the cost of going by there? It's like negative 5 cents. You've got this ice cream cone, right? Does everybody see that? What is the cheapest cost to get from here to here? What is the cheapest possible path? Okay, yeah? It involves eating an infinite number of ice cream cones. Does everybody see this? Okay? Because, although here the cost of going here would be seemingly minus 1 cent, right? You could do even better. Now it would be minus 2 cents. Now it would be minus 3 cents. Does everybody see that? So if you have negative weight edges in a graph, you might have negative cost cycles in a graph. And negative cost cycles in a graph are bad things. Not bad things. If you like ice cream, that's a great thing, right? But in terms of whether the shortest path is well defined, does everybody see that you could make the cost as cheap as possible by going through this loop as many times as you want? Okay? Any questions about that? For this reason, our algorithms, we're going to say that our algorithms are not going to, permit negative weight edges in graphs. Okay? Any questions? Is it, yeah?
I thought you weren't allowed to have cycles. There's a cycle there, so you wouldn't have done it anyway, would it?
What do you mean by that? Oh, you're saying that if my algorithm insisted that I'm not allowed to take any cycle, okay, you're saying then it wouldn't do this. Okay? Maybe, but I guess what I'm going to say is certainly if the graph was positively weighted, you're never tempted to take a cycle on the shortest path. Do you agree with that? It's clear that negative weight edges cause some funny behavior. Okay? And in order to minimize our problems, we are not going to allow in our shortest path graphs here negative weight edges. Because negative weight edges might lead to negative cost cycles, which might lead to funny behavior. Okay? If you view it normally as distance and you assume there is no such thing as a free lunch or a free ice cream, then this is not that big a constraint. Okay? But algorithmically it changes the problem. Yes?
Would, in that example, adding 5 to all the weights work?
Well, would adding a fixed amount to every weight vertex solve the problem? And I claim the answer is no, and it's no for an interesting reason. So let's maybe go through this, because this is actually kind of interesting. He is saying one way that I could solve my problem to get rid of that negative weight might be to add 5 to every vertex, every edge that is there. Does everybody see this? 7, 6. Okay? Does everybody see that creates another graph which doesn't have any negative weight edges, right? Might the shortest path change, however, by this thing? Okay? Do you see what he's done? He's saying, you don't want to deal with negative weight edges? Why don't we add a fixed amount to every edge to make every edge positive?